Welcome to The Explainer. Today, we are diving into a really fascinating puzzle happening on our very own sun. See, there was this massive current flowing across its surface, but then it just seemed to disappear, right where it should have been the strongest.
So picture this. The sun has this enormous conveyor belt. It's not made of rubber, of course, but of super hot plasma. And it flows across the entire surface. For decades, scientists had a pretty straightforward idea about where it went. But as we're about to find out, the sun had a major surprise in store.
So, what do we call this thing? Well, scientists call it the meridional flow. And trust me, it's a huge deal. This flow is one of the key engines driving the sun's 11-year magnetic cycle. You know, the one responsible for sunspots and those massive solar flares that can actually affect us here on Earth.
Think of it like this. In each half of the sun, there's this vast conveyor belt. It's slowly churning along, carrying magnetic material from the equator up toward the poles, moving at about 22 miles per hour.
For years, solar physicists had a clear, totally logical theory about what happens when all that magnetic material gets to the poles. But then, a satellite named Hinode sent back some brand new, incredibly detailed data, and it pretty much turned that entire theory on its head.
And this is where things get really weird, because it's a total contradiction. The old idea was simple, right? The conveyor belt carries magnetic stuff to the pole, so it should all pile up there and get stronger. But what Hinode actually saw was the exact opposite. The magnetic fields got weaker and more spread out the closer they got to the poles.
Okay, take a look at this. This is the data that kicked off the whole mystery. These are Hinode's maps of the sun's poles. See how the colored spots, which show the magnetic fields, kind of thin out right at the center? Right where those plus signs are. That's exactly where everyone expected to see a big, concentrated pileup.
So you can imagine scientists scratching their heads. The big question became, what in the world is going on with this flow? How could a current that's supposed to be dropping off magnetic material actually be making it vanish?
How do you solve a puzzle that's happening 93 million miles away? Well, you build your own sun, a virtual one, of course. Researchers turned to some seriously powerful computer simulations to create a digital lab for our star.
They use something called a surface flux transport model, or SFT for short. It's this incredibly complex simulation that accounts for the sun's rotation, how things spread out, and of course, that all-important meridional flow. And what was so cool is that for the first time ever, they gave the computer a very specific target. They basically said, look, your final result has to look exactly like the real sun that Hinode saw. All right, with their virtual sun fired up, it was time to start testing some ideas.
First up, the most obvious idea, what if the conveyor belt just, runs out of steam? What if it just stops somewhere around 70 degrees latitude, well before it actually gets to the pole?
They ran the simulation and nope, it was a mismatch. That R-squared value you see there is basically a score of how well the simulation matches reality. A perfect 1 would be a perfect match. This wasn't even close. So, theory number 1? Busted.
Okay, back to the drawing board. Hypothesis 2. What if we try the exact opposite? What if that conveyor belt doesn't stop at all, but just keeps on trucking all the way to the very tippy top of the sun? And oh boy, this was a terrible match. Way worse than the first one. I mean, that score went deep into the negatives. So the big takeaway here was clear. None of the simple, logical answers were working. Something else, something much more unexpected, had to be happening.
This is when they had to get really creative. They started thinking, what if we're looking at this all wrong? And they came up with a really wild idea. What if there wasn't just one flow? What if a small, second current was flowing in the opposite direction right up there near the poles?
And bingo, this was the aha moment. Just look at this. On the left, that's the real sun. On the right, that's the simulation, but this time with that tiny little counterflow added in. Suddenly, it's a near-perfect match. See how the patterns of red and blue just snap into place? It was an absolutely remarkable breakthrough. So just how small was this little counterflow that cracked the whole case? Get this. Its max speed was only 3 meters per second. That's it. A tiny, almost unnoticeable detail that turned out to be the key to the entire mystery.
Okay, so what does this all mean for our understanding of the sun? Well, it basically means we have to redraw the map of how things move around on its surface.
It turns out the system is way more elegant than we thought. You've got that main conveyor belt flowing from the equator, but it stops around 70 degrees latitude. And right there, a second, smaller circulation cell takes over.
And on the surface, this little cell flows away from the pole, effectively pushing the magnetic fields back and creating that thinning effect Hinode saw.
The researchers themselves put it perfectly. They said the two flows meet at the solar surface with the latitude of plus or minus 70 degrees and return in the subsurface. So it's not one big loop in each hemisphere, it's two.
So why should any of this matter to us? Well, here's the thing. This flow is the fundamental engine of the solar cycle. And that cycle is where it creates space weather. You know, the solar storms that can mess with our satellites, our GPS, and even our power grids right here on Earth. By solving this mystery, we don't just get a new map of the sun. We get a much clearer insight into its engine and a much better shot at predicting its behavior and preparing for its awesome power.